All right, everybody, so this is on page 9 of your unit handout. What you're going to be looking at in this lesson, we've only got 2 examples, but one of them is quite involved, is how to determine the area between multiple functions. And this can range from things that are really quite simple, like example number 1, to something more complicated, like example number 2, to something even more complicated. So the first example says find the area between these 2 curves. Now, I know that y equals 1/2 x plus 4 is a straight line, but we still can refer to it as a curve. Can you confirm that those functions match what you have? Okay. So, I mean, think about this for a second. You know that this is a parabola. You know that. You know that this is a straight line. So, if I said to you, find the area between the curves, and this is what they looked like, you understand that that's a bogus question, right? Like bogus meaning it's dumb. You can't answer that question. It's not a fair question. Because the answer to that question would be infinity. So it has to be the case that what we're talking about, and we are not using our graphing calculator, that what we are talking about is something that must look like that. It has to. So what we need to do is get a visual picture of what this graph looks like, both of these graphs. Now we have a general idea of what these things look like. This is a parabola that opens up. We don't really have much information about where it is unless we either do a chapter 5 analysis or complete the square, and we're going to have to do something. Well, I don't want us to use our calculator here for this one. And we know that this is a straight line with a y-intercept of 4 and a slope of 1/2. Well, let's start with that. Let's do a rough sketch of the linear function. The y-intercept is 4, and it has a slope of 1/2. So what does a slope of 1/2 look like? Not that it really matters. It's a positive slope, and 1/2 is a slope. Means you go 2 to the right and 1 up. That's going back to a very basic definition of slope from even grade 9 or 8. So it's a line which is not too steep. All right, so if we were to sketch this, it looks approximately like that. It doesn't have to be perfect. Now, rather than do a whole chapter 5 analysis, which nobody wants to do, and rather than completing the square, why don't we just find the minimum value of this function? We know it's a parabola that opens up. And if the parabola opens up, that means there's a minimum value of the function. How do we find the minimum value of the function? Well, we can take the first derivative and set that equal to 0. And boy, don't you wish you could solve Math 20 problems that way to find out where the vertex of a parabola is instead of completing the square. The derivative of this, I don't even need to write equals 0. The derivative is 2 times x minus 2, which means that the vertex of this thing is at 2 comma something. Well, 2 comma what? Does that make sense that the vertex has an x-coordinate of 2? Because that's the minimum of the function. That's the only critical point of the derivative. So we put 2 into the original function, and what do we get? You get 4 minus 8 is negative 4 plus 6. I think you get 2. You get 2. So let's just confirm something here. So it's a 2 comma 2, but let's confirm something. Let's put x equals 2, the coordinate of the vertex, into the linear function and see what we get. So 1/2 times 2 plus 4 gives you 5, right? Why am I doing this? To confirm that the vertex of this parabola, which is at 2 comma 2, is in fact below this line. This, if you're keeping score, is at 2. Here's 3. 4, and there's 5. So this is up at 5 somewhere. All we've established here, and you don't need a fancy diagram. All we've established is that the parabola and the line look something like this. So if you want to determine the enclosed area, then you're asked to determine this area. And on any kind of written response question or assignment, certainly at the university level, you would be required to include a sketch of the problem as well as the solution. So this is y equals 1/2 x plus 4. And this is y equals x squared minus 4x plus 6. Well, you don't know how to find that area between the x-axis and a single function. We'll get to the solution in a bit. But what you do need to figure out is where these two functions intersect. I think you would agree, regardless of whether you personally have figured out the solution to the problem and what to do. I think you'd have to agree, we have to know where that area begins and where that area ends. So what we're going to have to do is find out where those two functions intersect, and that means we are going to solve this equation. X squared minus 4x plus 6 equals 1/2 x plus 4. They intersect where their two y coordinates are equal. We solve that equation. I'm going to multiply both sides of the equation by 2 because I don't like dealing with a fraction, and get 2x squared minus 8x plus 12 equals x plus 8. Double check my work. 2 times x squared is 2x squared, negative 8x, 12. Looks okay. Zero it, of course, because it's a quadratic equation. And you'll get 2x squared minus 9x minus plus 4. Look okay? Is it factorable? Well, we'd have to do the b squared minus 4ac thing. Or some of you are lightning quick at factoring. You could just factor it and see. B squared minus 4ac is 81 minus 32 is 49, I believe. And 49 is a perfect square, so it's factorable. That makes our lives easier. That means whatever numbers we have, they're not going to be irrational. They're going to be fractional, I'm assuming. This is an interesting one. If we know it's factorable, it has to be x and 2x. No, there's no choices. With the 4, we have two options. We can go with 2 and 2, which I immediately throw out. I can't have 2 and 2 to give me the 4, because then I would be forced to put a 2 in the first binomial, creating a common factor of 2 where none exists. Okay? Which means it has to be 4 and 1, and I can't put a 4 here. So it's got to be 1 here and 4 there, and they have to both be negative. We can, of course, a huge mistake there. Not a mistake, but omission equals 0, right? Of course, you can FOIL it out and confirm that that works. So we have x equals 1/2 and x equals 4. That's what we are dealing with. So now the question is, how do we find the area? And I'm going to give you a minute or two to think about this, and I'm going to give you a better picture to help in your pondering. What we are trying to do is find that area. And you have all the tools that you would need to find that area, but I'm going to give you a minute to see if you can figure it out. And I am in no means rushing you, but I'm always curious. How many of you know what you need to do here to find the area? One person so far. One person who says, yes, for sure, I know what to do. And it's not a race. How many now know? 2 in total. I could give you some hints, and by the way, what you're trying to figure out here, everybody, is not something that, for the next example, you're going to have to spend 5 minutes thinking of as well. You're thinking of something that's going to work all the time when you have 2 functions like this. I'll start giving you hints. And once I give you the hints, more and more people will very rapidly understand what it is they need to do. So let's forget about that area for a second. In fact, let's even forget about that function. Let's not worry about the linear function. Do you know how to find this area? You should, because that function you're looking at is above the x-axis and is positive everywhere as well as being continuous. You know how to find that. So, but now let's forget about that function. Let's go back to this. Do you know how to find that area? Sure. That area would be the antiderivative of that function from 1/2 to 4. This area would be the integral of that function from 1/2 to 4. If we put them together, and it's kind of confusing, but this is the area under the red function. This is the area under the brown function. This is the area we're asked to find. And it's kind of like a literal puzzle here. The area we're asked to find would be this whole area minus this area. It would be the area below the upper function minus the area below the lower function. And that's a really good thing to kind of remember here at this point, is that as long as we have one function above the other, from, say, x equals a to, say, x equals b, this area should be equal to the integral from a to b of the upper function minus the integral from a to b of the lower function. We'll talk later about the fact that, strangely enough, it doesn't matter where these are. They could both be below, they could be partly above, partly below the x-axis. It's not going to matter. As long as you use upper minus lower, you will get the answer. That's what we need to do. Now, we're going to do this, so that's what I have there. Right, that's in your notes. So now let's do this with this example. The upper function is 1/2 x plus 4. So I need to take the integral from 1/2 to 4 of 1/2 x plus 4 dx and subtract the integral from 1/2 to 4 of, help, x squared minus 4x plus 6? I got it. So did I write the two functions down correctly? And it is what you need to do. Now here's where things get really messy, because anti-differentiating is no problem. We anti-differentiate 1/2 x plus 4. I don't mean it's no problem like it's really easy. You have to think about these things. The antiderivative of 1/2 x is 1/4, nope. Yep, 1/4 x squared plus the antiderivative of 4 is 4x. I guess I'll try to be precise in my writing here. This is from 1/2 to 4. Do me a favor and just confirm to yourself that the derivative of what I wrote will in fact give you 1/2 x plus 4. Okay. Minus, well, what's the antiderivative of this function? It's x cubed over 3, or 1/3 x cubed, minus 2x squared plus 6x, evaluated from 1/2 to 4. Again, take a second and confirm that my antiderivative is correct by differentiating it to see if you get what I was anti-differentiating. Now where things get a little bit messy is that we're taking those two things, those two terms, and we're going to subtract them, but each of them is found by subtracting two things. Right? We need to put in 4 into this expression and get 1/4 times 4 squared. We'll actually have another set of brackets here. So I'm going to put in 4 and subtract what I get when I put in 1/2. Then I have to subtract this one, which will be what I get when I put in 4 minus what I get when I put in 1/2. See what I'm getting at here? There's a lot going on. A lot of numbers. So evaluating just this would be 1/4 times 4 squared plus 4 times 4 minus 1/4 times 1/2 squared plus 4 times 1/2. Then I'm going to have to take 1/3 times 4 cubed minus 2 times 4 squared plus 6 times 4 minus, I do the same thing at 1/2. I double check everything. I mean, what I'm doing when I'm double checking this is I'm looking at things visually like this. Ugh. I'm looking at all of that. And am I seeing 1/4 times the thing squared plus 4 times the thing? Yes. Both 4s, both halves. And then I'm looking at the same idea here. And then what I'm going to be doing is calculating 4 different things. And just so you know, if I ask you to do this on an assignment, and in university it would be the same, you cannot just say now equals and give me the answer. Okay? That's just a hair away from just saying, oh, this is equal to something. You have to show the numerical steps. So I want you to start working on all of that. I'm going to do the same thing up here. 16 over 4 is 4, plus 16 is 20. That's 20 minus. I don't know about the last one. Can you help me out with the last one? Is it? I got kind of weary there. Is it 20 minus 33 sixteenths? Is it 40 thirds? This one I just gave up at the end. I feel bad. 60, 61? So is that right, Cadbury? Okay. So, you know, my brain is just hit, not a breaking point, but you know, sometimes it's okay to use a calculator, even if you know you're not supposed to. 20 minus 33 sixteenths gives me 287 sixteenths. Minus 40 over 3 minus 61. And I don't mistrust you, Cadbury, but can somebody else confirm 61 over 24? Okay, I just wanted a few people before I commit to it. Yeah, my brain would not be able to handle that. We in agreement on those two numbers? Okay. Look at the thing. You know what the thing that's probably the most difficult about this problem is? Is numerical fractions. Junior high math is probably the thing that's, if you're going to get this wrong, this is where your mistakes will lie. But I have good news for you. The answer is 343 over 48 square units. The good news is there is a property of integrals that says this. If you have an integral from a to b of one function plus or minus, in this case I'm going to use minus, an integral from a to b as well of a different function, then you do not have to figure out two separate integrals. It turns out that the integral of one function minus the integral of another function is equal to the integral as long as it's from the same number to the same number of the difference in the integrands. What does this mean? It means that rather than doing this, we can do this. And it means rather than, I'm going to go back to our work here, which is a boatload of work. Rather than doing this, everything that we did here, which is a real pain, we can do the following. We can do one integral from 1/2 to 4 of 1/2 x plus 4 minus x squared minus 4x plus 6. In other words, rather than anti-differentiating both of them and then calculating them both and subtracting them, we can subtract the functions first and then anti-differentiate one function. So if I do that, let's just see what happens. And then we'll do the next example, which is a little bit more complicated. but maybe not as much work as this one because we're not going to do the two integrals separately. This would be the integral from 1/2 to 4 of, okay, wait a minute. Look up here. 0x squared minus x squared is negative x squared. 1/2 x minus negative 4x is 4.5x or 9/2 x. And 4 minus 6 is negative 2. Well, let's anti-differentiate that. If you like, I've multiplied -1 through here and then simplified the result. One plus 4 is 9/2, isn't it? Okay. So are we satisfied with the algebra there? I'm not seeing a lot of people nodding, so I'm not sure if you're with me on this or not.
I just have a question from the previous part. For the last part,
Yeah.
I got 85/24.
Oh, for the answer.
Yeah, but when you were asking, not 61/24, but I'm not sure if I'm doing something wrong. Is that what you got as well?
I thought I had 85/24. That's what I thought I wrote to begin with, but then I asked, and a couple people said 6. So we're talking about this.
Yeah.
Okay, so let me recalculate this. Is your question about the same thing? I can't hear you. I'm sorry.
There it's negative 2, 4 to the squared, and then there's positive.
Oh. So I bet you did the positive and I did the positive, right? We'll find out. So this is negative. So, well, let's calculate this again. I'm guessing it's going to be 61/24. Yeah, it is. That's why I got 85/24 was I was using a positive. So the correct answer is, in fact, 343/48. Okay. So now I want to go back to my question here. If we subtract this first, I'm just asking you to confirm that we do get negative x squared plus 9/2 x minus 2. Okay, so we're going to anti-differentiate that. And you can see what happens. I hope you can see what's about to happen. We're just going to have something minus something. That's it. We're not going to have something minus something minus something minus something. We're going to have negative 1/3 x cubed plus 9/4 x squared minus 2x from 1/2 to 4. And I hope you see that that's going to be an easier calculation. It's half the work. I don't think we need to write everything down here just to convince you that this is the way to go. I'm actually going to eliminate errors. Is my antiderivative correct? I'm going to put it in for y and just use my table to generate the values at 4 and 1/2, and then we can go from there. Plus 9 divided by 4 times x squared minus 2x, 1/3 x cubed plus 9/4 x squared minus 2x. My table is set up to allow inputs, so I'm going to put in 4, and I get 6.6 repeating. I'm going to put in 0.5, and I get negative 0.4792. 1, 0.66666, 4791, negative 0.4791. Luckily, it worked. The other one was 6.6 repeating. A lot quicker. I mean, it was quicker because we cheated a bit near the end here on our calculator, but it's a lot easier if you subtract the two integrands first. All right, you want to take a little break, or do you want to move on and do the next example? The next example is going to be about 20 minutes at least. Who's for taking a break? Let's take a 5-minute break. Okay, just a little break. So once again, everybody, this is what we do in terms of making sense of the problem. We say that since one of the functions lies entirely above the x and is entirely above the second, if we find the area below the upper function and subtract the area below the lower, we get the area between them. But this is more practical. It loses some meaning. Like when you subtract those two functions, what are you actually getting? Well, you can use your graphing calculator. If I were to graph the difference between these two functions, if I were to graph y equals the linear function minus the other function, I would get, and if you look up here, I'll show you, I would get a parabola that opens upside down and has an x-intercept here and here, and this area here would exactly be equal to that area. You'd find it would have the exact same x-intercepts. Of course it would, because those two things are equal to each other on the x-axis. Now, one thing I have to address is it doesn't say anything on this screen that you're looking at about being above the x-axis. And the reason is, if this is what it looks like, I don't care where this stuff is, if it looks like this, and I ask you to find, I won't do two at once, I ask you to find the area between those two functions, you're still going to go upper minus lower. And the reason is, even though those two functions do not lie entirely above the x-axis, if you add some number to each of those functions, and you add the same number, what you will be doing is shifting those two functions up the same amount. The area between them will still be the same, and they are now both entirely above the x-axis. You know, you might say to yourself, well, yeah, but now the antiderivative is going to have an extra term of 12x, but it's 12x minus 12x. It's upper minus lower. You're going to subtract those two constant terms, so it won't even be in the antiderivative. And it doesn't matter where the functions are. Okay, so let's take a look at the final example here. What is the area between the curves y equals sine x and y equals cos of 2x? I'm trying to decide whether we should maybe just rely on our graphing calculator for this one. Let's do that. Okay. I mean, very quickly, I'm not going to rely too much on paper, but very quickly, you should know that y equals sine x looks like this. Y equals cos of 2x stretched by a half looks like that, you should be able to graph them and find intersection points. But let's save ourselves a little bit of a heartache this afternoon and use our graphing calculator. So we want to know what this looks like from negative pi over 2 to 5 pi over 6. Y equals sine of x. And y equals cosine of 2x. I'm going to go zoom trig to begin with to get a visual of this. That's what it looks like. I'm going to go into my window settings now and start at negative pi over 2. And go to 5 pi over 6. To get a visual. I'm also going to play around with the other window settings a little bit for vertical to spread it out a bit. It's looking like that. I'm going to go from negative 2 to 2 just to widen it vertically. So one observation that I make here is it appears that they intersect at negative pi over 2. And it appears that they intersect at 5 pi over 6. But we want to verify that. I would verify it by going into my table and entering negative pi over 2 to see if y1 and y2 are the same. They are. So we're not even going to solve this algebraically. We could set sine of x equal to cos of 2x and solve that equation. I've run out of energy for something like that this afternoon, and I think probably you have too. You would have to use a double angle identity. It's not difficult. It's just more work. Let's also confirm, because it appeared as though they intersected at 5 pi over 6, and they do. And they intersect at one other place, so let's find out the coordinates of that by going to our calculate menu and choosing intersect. I mean, I don't know why it put me right there to begin with, but okay. First curve, y equals sine x. Second curve, y equals cos 2x. It intersects at that number. Now, wait a minute. What is that number? That's a number of radians. But look, we should be able to figure this out. This is pi radians here. If you were to look at your window settings, oh, it's actually maybe pi over 2. Let's just confirm something here. I'm going to go trace. Well, I'm going to scroll, actually. It's just as easy. I'm going to go over to this tick and see what number it is. Yeah, that's pi over 2. Half of pi is about 1.57. So it looks like that's probably pi over 6. We can confirm that by going into our main menu and taking pi divided by 6. Was that the number we saw at the point of intersection? I believe it was. So what we have learned from that little exploration is they intersect at x equals negative pi over 2. They intersect at x equals pi over 6. And they intersect at x equals 5 pi over 6. We need to solve this problem with two areas. For area 1, this is cos of 2x. And for area 1, cos of 2x is above sine of x. Give that some thought. Like, look at this area here that I'm highlighting with this brown border. What is above is the upper function, which is cos of 2x. So that first area will be an integral from negative pi over 2 to pi over 6 of, we're not going to find the integral of the upper minus the integral of the lower. We're going to find the integral of the upper minus lower. We're going to subtract the two functions. So we're going to have cos of 2x minus sine of x dx. This is the upper. This is the lower. When we take a look at this area, which also is an enclosed area by the functions, call it 2 if you like, it is an integral, and it is from pi over 6 to 5 pi over 6 of, we have to have upper minus lower. Well, what is upper now is sine of x. Sine of x is what's on top now. So it is going to be sine of x minus cosine of 2x. So, you know, imagine what would happen if you didn't subtract the integrands first. You would have, for the stuff written in brown, the integral from negative pi over 2 to pi over 6 of cos 2x dx minus the integral from negative pi over 2 to pi over 6 of sine x dx minus, in brackets, the same kind of mess over there. And each of those integrals, each of those 4 integrals, is going to have something minus something. You know, how often do we forget to carry a negative in when we're subtracting? It's going to be impossible to keep track of them. At least now we're increasing the odds of success. All right, so that's the nice thing about this is the anti-differentiation is not difficult. The antiderivative of cos 2x is 1/2 sine 2x. Minus, what's the antiderivative of sine x? Well, what do you differentiate to get sine? You differentiate negative cos, which means, and we're going to double check this. I have to, which means I believe that when we go minus the antiderivative of sine, we're going to have plus cos x. So we differentiate that and convince ourselves the derivative of 1/2 sine 2x is cos 2x. The derivative of cos x is negative sine x. Excellent. This is from negative pi over 2 to pi over 6. We don't even really have to think too much here. It's going to be the opposite of what we have. Instead of having positive cos, we're going to have negative cos. And we're also going to have negative 1/2 sine 2x. So let me write this stuff down here first, and then I'll explain something. So the antiderivative of sine is negative cos. The antiderivative of negative cos of 2x is 1/2 sine of 2x. I said they're going to be opposite because we're subtracting them in the opposite order. So it was a minus b becomes b minus a. Everything is opposite. Any questions to that point? Okay, so there's nothing that can be factored out here. We are going to have 1/2 sine of 2 times pi over 6 plus cos pi over 6 minus 1/2 sine of 2 times the negative pi over 2 plus cos of the negative pi over 2. I'm going to take a breather here and double check that. So again, what I am doing here, everybody, it's a tip, and I don't know whether you find it helpful or not. I'm just doing this. I'm just confirming my substitution matches that I put in for x pi over 6, and then I put in for x negative pi over 2, and I'm subtracting. The green set of brackets that I have is really not necessary, but I want to impress on you that that's the whole first part. This next green set of brackets is also not necessary because I guess I'm adding, I'm not subtracting. But I'll leave them there anyway. Now I'm going to have negative cos, and my upper is 5 pi over 6, minus 1/2 sine of 2 times 5 pi over 6. Minus the same thing with pi over 6. I would say the biggest obstacle here to getting an answer, to being successful, is that you just need to try to be as organized and focused as possible. There's just so much going on here. So now I write the same thing, negative cos of the lower, which is pi over 6, minus 1/2 times sine of 2 times the lower, which is pi over 6. And again, I'm going to take a minute and compose my thoughts and check. I've got negative cos of the argument. I've got negative cos of the argument, negative 1/2 sine of 2 times x. So I put in 5 pi over 6. Looks good. I put in pi over 6. Looks good. Now we have to figure out what this is and put them together. These two, put them together, etc., etc., etc. So now we're looking at the unit circle unless you've got it burned into your skull. I'm going to continue here by having these 4 main pieces separately. And you're going to double check as I'm talking my way through this. 2 times pi over 6 is pi over 3. Sine of pi over 3. Okay. Sine of pi over 3 is root 3 over 2 times 1/2 root 3 over 4. Plus cos of pi over 6. Root 3 over 2. I'm going to pause here and ask you to confirm that these two things are in fact these two things. Good. And you're looking at your unit circle here. So, if I were writing an exam, I would be looking at the unit circle too. I wouldn't be trying to visualize it in my head. 2 times negative pi over 2 is negative pi. Oh, good. Negative pi takes me here. Sine is 0. Times 1/2 is 0. Cos of negative pi over 2, jackpot, 0. I mentioned this yesterday, I think, don't try to connect any significance to what that means. Don't, you'll go crazy. Then I'm at negative cos of 5 pi over 6. So cosine of 5 pi over 6 is root 3 over 2. It's actually negative root 3 over 2 times the negative in front of the cos is root 3 over 2. And then we have minus sine, minus a half times sine of 2 times 5 pi over 6, which is 5 pi over 3, which is 1, 2, 3, 4, 5. The sine of 5 pi over 3 is negative root 3 over 2 times this negative 1/2 gives you negative times a negative is positive root 3 over 4. I want to double check that. Negative cos 5 pi over 6. Well, cos 5 pi over 6 is negative root 3 over 2 times negative is root 3 over 2. 5 pi over 3, 1, 2, 3, 4, 5 is negative root 3 over 2 times negative a half. It's positive. Yes? Okay. I seem to have a feeling in my head that this set of numbers should be equal to this set. I don't know why I'm saying that, but to me it kind of makes sense because these two integrals are the opposite of each other, although the numbers are different. Negative cos of pi over 6. How can you not know that? Cos of pi over 6 is root 3 over 2. Negative root 3 over 2. Because it's negative cos. I suppose we could have moved those negatives in. This is pi over 3. Sine of pi over 3 is root 3 over 2. Times negative a half is negative root 3 over 2. No, is negative root 3 over 4. Distributing that negative, I get that. So what I see is I have a root 3 over 4 plus a root 3 over 4 plus a root 3 over 4. If I remove all the brackets, I have this. So I have 3 root 3 over 4s, and I have 3 root 3 over 2s. Common denominator time, multiply the top and the bottom of this fraction by 2 to get for an answer 3 root 3 over 4s plus 6 root 3 over 4s, which is 9 root 3 over 4. I want to check it on the calculator. There's two reasons why I don't want to check it. One is I'm scared that it won't be wrong. I don't know what the other reason was. Maybe there's only one reason I don't want to check it. But I already have them in here, so what the heck? I'm going to go, how do I check it on the calculator? Wait a minute, this is interesting. Because I got two functions. The only way for me to check it is to sketch now upper minus lower. I have to sketch this and evaluate it from negative pi over 2 to pi over 6. There's a way to do both of them at once, but it's kind of complicated. So cos of 2x minus sine of x. This is kind of interesting to look at too. Do Do you remember what I said about if you were to sketch the difference, they will have the two x-intercepts of the upper and lower? Well, this is negative pi over 2. That's pi over 6. By the way, this is the other area, but it's below. So if I went absolute value, I could do it in one shot, but I'll do it in steps first. It was from negative pi divided by 2, correct, to pi divided by 6. 1.299. Now, if you wanted to check the other one, technically you have to sketch this. And by the way, as I'm walking through this with you, I think there's things that you're learning by looking at the graphs. I think it's a good learning experience. So I need to reverse this now. Of course, this graph is just going to flip over, isn't it? So sine of x minus cos of 2x. And we're going to calculate an integral, this time from pi over 6 to 5 pi over 6. There's that area now that we found before that's now negative because we flipped the integrand over. You get 2.598. Help me out. Did we have 9 root 3 over 4 as an answer? Suspense is killing me. If you add 1.299 and 2.598 together, it works. By the way, you could have, and whether, if you understand what I'm about to tell you, you really get what's going on with the positives and negatives. I could have done this. If I graph the absolute value of that function and just go, what is the integral from negative pi over 2 to 5 pi over 6, I'll get the answer because it flips any negatives up. So this is going to go up. It's going to touch the x-axis, and then it's going to go up again. Negative pi divided by 2 to 5 times pi divided by 6. So this should give us that whole answer of, I forget what it was, 3.8. I don't know what it was, 3.58 something. 3.897. I bet you that calculator is really quick, eh? Or does it still grind away? Oh, okay. It's quicker though. It's still kind of slow. There's a lot of calculations that it's doing here to find the answer. So now what? Well, on page 462, question 1, are a variety of problems. Now, some of them are really interesting. Like one of these ones in the challenge problem is 4 lines. What is the area enclosed by the 4 lines? So if you were to sketch the 4 lines, they might look like this. And what you would then have to do is say, you know what? From the brown dot to the red dot, from the brown dot to the red dot, line 1 is above line 2. So I'm going to go the integral of line 1 minus line 2 from whatever this x coordinate is, which you have to find by setting the equations equal, to whatever this x coordinate is. From the red dot to the green dot, line 4 is above line 2. So you have a different integral to work with there. And then from the green dot to the black dot, line 4 is above line 3. They're not all like that. That's why that's a challenge problem. But there's some basic problems where you have two functions that are making an area by an enclosure, and then they get more difficult and more difficult. The idea here is you want to be able to solve at least the basic ones. Within the next half hour or so, I'll give you your assignment for Unit 4, and in the meantime, you can get started on that. And give me a few minutes to just get things organized, and then I'll be able to help you out.